So let's talk about 11.7. Again, take 3. Okay, so what we want to do is we want to describe a population, right? And we've got some kind of model for this. Okay, so our kind of model for this is we've got this rule, P, that takes times in and outputs populations. So here we're going to think this is population as a function of, what's T? Probably time, yeah. Okay, and there's a formula for this, and it's given by this kind of funky looking P with a 0 subset, a 0 subscript. It really just is one symbol that means population at time 0. Okay, so when we look at that, we think pop at T equals 0. And then there's this other business of, oh, there's an E to an R and a T. So what do I kind of think of when I look at E?
It's a constant.
Yeah, E's a number, right? It's like pi, it's a little bit funny, but it's just a number. Okay, and then R is this thing that we're going to think of as a growth rate. And then this T, that's going to be our time, right? Okay, so this is the kind of PERT, I think is usually the acronym you might memorize for continuously compounding growth. So stuff that follows this model are little bits of bacteria in a petri dish, or people in the world, or radioactive decay, or investments, or kind of a bunch of things, right? As long as it's kind of growing continually and doesn't have some kind of cyclical reproductive cycle, like frogs are a crappy example for this, because they reproduce once every year in the spring. They don't really grow continuously. They kind of spike once every once in a while. Cool? All right, so we maybe tried an example with this. We'd say something like, give a model for a population of, I don't know, what's a critter that doesn't have that cyclical behavior?
Mice.
Mice? Cool. Okay, so we've got a model for a population of mice that starts at 120 mice and grows at 5% per year. Okay, so if we want to give a model for this, and this is the kind of complaint that I had, that this 5% per year thing is a growth rate, right? Now, doing this honestly with like really good science, this is not quite the same thing as R. But your book makes this assumption that it is, so we'll play along with your book. So playing along with the book, this is our R. Wait, how do I turn 5% per year into an R?
It would have to be like 0.05 because it's a percentage.
Okay, great. So let's see, we want to talk about P of T, right? Okay, so this should be, what did we think when we looked at the P0 symbol? What was that thing?
That's when population, that's what the population is at time 0.
Yeah, that's kind of the population you start with, right? So if we're starting with 120 mice, that's our starting. And then we've got E. Do I have to fill E with something? Why not?
It's a number already?
Yeah, it's already a number. You can't plug it. You can't make it any more numbery, right? And then, okay, I need the R. The R on this one's 5%. So I need to turn that into an honest kind of number. So what's 5% as a number?
0.05.
Okay. So we put in 0.05 t. And then we might use this to answer questions like, how long until the population doubles? So how do I figure out how long until the population doubles?
Would you take the right half of the equation and set it double to the starting, which would be 240, and then solve for t?
Yeah, really I'm wondering, right, when is P of t equal to double my start was 240, right? So I'm setting P of t equal 240 and solving. So I've got kind of this question, right? I'm wondering, when is P of t 240? Well, P of t is this other thing, so that's when is 120 e to the 0.05 t. When's that 240? So what do I do both sides?
Divide by 120.
Okay, we're trying to solve for t, right? So we divide by 120. That'll get us e to the, what?
0.05 t.
Okay, 0.05 t, and that's supposed to be 2. Okay, so then what? Where's your t stuck and where do you want it?
You want it like on ground with like the 2 and all that stuff. So
Yeah, I want like t equals stuff, right? So what's hanging me up?
that E.
The e, right? And the fact that my t is little. Okay, so how do I get the t out of the little corner it's stuck in?
You have to log everything.
Yeah, you log both sides, right? Okay, so if I log both sides, I'll get
0.05 t equals log 2, or log to the, yeah.
natural log of 2. Okay, cool. Okay, then what?
You divide 0.05.
Okay, we could divide by 0.05, so we get t equals, let's divide 0.05. So I get t is what?
ln 2, natural log of 2 over 0.05.
Okay, natural log of 2 over 0.05. That's probably not very convenient, right? Like this doesn't tell me t.
No, then
How do I get it?
Gets the like an approximately on use a calculator.
Okay, right, it's really a model anyway, right? So it's not really actually the truth about the mice anyhow. So when I get to here, certainly I'm willing to approximate because I was already approximating the mice anyhow. So what do I get? You get something now?
ln of 2 is 0.0693.
Okay, so I got 0.0693 divided by 0.05.
Or maybe not. Maybe it's 0.693.
Yeah, I hope it's not 0.06.
Divided by 0.05 is 13.86.
Okay, so I got t is approximately 13.86.
And that's in years.
Ah, yeah, and that's in years. Why is that in years?
Because it's 5%.
Yeah, because they forced that on me. You guys see that? I adopted their units. If I had wanted to make it days, what would I have had to do?
Do 365.
Yeah, I would have had to
Multiply that by
rescale somehow, right?
And then you have, but with that, you also have to factor in the years.
Have to factor in what?
Wouldn't you?
No,
Not-
forget
Forget
that.
that.
Ignore leap years forever. They don't exist. Fake on your imagination. So, this was a question though, right? In words? What did I answer with?
A number.
crazy geeky symbols, right? So if I want to answer in words, how do I do that?
You would write the mice will double in a little under 14 years.
Okay. So how long till the population of mice doubles? Just under 14 years. Right, or approximately 13.86 years. You guys cool with that?